All right, we are back with the second lecture of chapter 6. And in the second lecture, we're going to talk a little bit about equilibria and kinetics. So equilibria, is a thermodynamic feature of chemistry. And then we'll get into kinetics, which is sort of the next kind of consequence of that. So again, this is going to be review from general chemistry. We'll go through it a little bit more quickly than we would otherwise. But make sure, slow down, pause the video whenever you need to. Ask me questions in the comments below, and I will get back to you right away. So, okay, so when we consider equilibria, what that means is basically like, rather than looking at a reaction as going from reactants to products, we have to instead consider the fact that a reaction can go either way. If an energy pathway can be used to get from the reactants to the products, then theoretically it can be used to get from the products to the reactants. In other words, when the forward reaction occurs, the reverse reaction can also occur. Now, when you have a spontaneous reaction where we have an exergonic reaction, just like what we're looking at here, where the products are lower in free energy than the reactants are, this tells us that there's essentially like a thermodynamic driving force. The molecules are going to want to be over here with at C and D rather than at A and B, because they're going to be releasing energy, and that energy is going to be increasing the entropy of the universe, which is again just kind of like a principle. It's like anything that happens spontaneously has to increase the entropy of the universe in one way or another. So now what that means is like this spontaneous process is going to result in more products than reactants, but the reverse reaction can still occur where you can have some of C and D colliding together to produce A and B. So now, ultimately though, so the exergonic processes don't give us 100% of our products. We still have reactants at equilibrium because as we decrease the concentration of A and B, in other words, as they react together to give us C and D, we're not going to have A and B just floating around in solution anymore. And remember, for a reaction to actually occur, the two molecules have to collide. There has to be a physical interaction of the two molecules. And if there's just none floating around, then it's not going to happen. It's improbable for that to happen. On the other hand, you are increasing the number of C and D molecules, so your products basically, that means that as that number increases, there's a greater chance that those are going to hit each other, and they're going to hit each other with enough force and with enough kinetic energy to actually reform the reactants. Eventually, you'll get to this point where the forward and reverse reaction rates are equal, and that's the state of equilibrium. And that's the minimum value of free energy that you get here. Okay, so just a quick review of the math of equilibrium. Remember that an equilibrium constant is equal to the concentration of the products divided by the concentration of reactants. For the reaction that we just saw, it was we have the concentration of C times the concentration of D divided by the concentration of A and the concentration of B. We also have this relationship between delta G and K, where the delta G of a reaction is equal to negative R, the ideal gas constant, times the temperature in Kelvin, times the natural log of the equilibrium constant K. So all of these that we've discussed, equilibrium constant, delta G, delta H, and delta S, these are all thermodynamic terms, and they're only really describing the relative stability of products versus reactants. Keep in mind the rate thing, that's going to be kinetics. We'll review that here in a little bit. This is a really handy thing. This is something that my grad school professor told me not that a long time ago, I don't know, a while ago, I'll just say that basically if you decrease the value of delta G by about 6 kilojoules per mole, that gives you about 10 times change in the equilibrium constant. So like, for example, if you start at a delta G of 0, that means that the equilibrium constant has to be 1, and that gives you a 50-50 split of reactants or products. If you go down by 6, so you go to negative 6 kilojoules per mole, that increases the KEQ now to 10 to the 1. So this is 10 to the 0, goes to 10 to the 1, and gives you a 90% concentration of products at equilibrium. Go another 5 to 6 to negative 11 kilojoules per mole. Now your KEQ is 10 squared, or 100, and then your percent of products is 99% at equilibrium. This is a really handy method of figuring out like how much of your products and how much of your reactants are going to exist at equilibrium. Okay, now talking about kinetics. So remember, kinetics is something completely different. We're going to be able to read it off of energy diagrams, just like we did for delta G, but it's not a state-based process where you can just look at the products, just look at the reactants, and figure out your value from there. So the negative sign of delta G tells us that a process is product favored or it's spontaneous. It'll go to the products, but it doesn't tell us how fast it's going to go. So in other words, like you can't predict how fast a process will occur, even if it is spontaneous. Like for example, iron resting is spontaneous at room temperature and normal liquid conditions. Yet it doesn't just rust on its own. Like you may have pieces of iron around, you have pieces of metal around. They don't just rust on their own. It takes a long time for them to rust. We don't see that happen in the blink of an eye necessarily. Other spontaneous processes do occur quickly. So like things that explode, that's a spontaneous process and it occurs very quickly. Another thing that is spontaneous but takes a long time is the degradation of diamonds. So diamonds are slightly less stable than graphite, for example. So if you take carbon in the form of a diamond and you let it sit out at room temperature, it will slowly unravel itself into graphite. But it takes like millions of years really to do that. So it doesn't really go very fast. Okay, so there's going to be 5 different factors that tell us that are going to affect the rate of a reactant. And these are all the things that we need to keep in mind as we talk about the rates of reactions moving forward. Number 1 is going to be the concentrations of the reactants. 2, activation energy. 3, temperature. 4, sterics. And then 5, catalysts. So we'll talk about each of these kind of in turn. Starting from kind of the most familiar one, which is basically how does the concentration of reactants affect the rate of the reaction. To do that, we have to remember what a rate law is. And remember, the rate law is going to tell us that it's going to give us a way of determining what the rate is for a given reaction, like how fast is the reaction going to go. And the rate is equal to a rate constant K that has to be determined experimentally times the concentration of the reactants. Now, you may recall from your Gen Chem 2 class, I hope you remember this, that just because you have a set of reactants in a reaction doesn't mean that the rate of that reaction is going to depend on the concentration of those reactants. You need to figure out the order of the reaction by determining the elementary step, which you're going to figure out with the mechanism. Now, fortunately, we're in a position now in organic chemistry where you're going to be looking at mechanisms, and we're going to look at individual steps in a reaction. So we're going to be breaking down things into elementary steps anyway. So this kind of puts us on a good footing for using these rate laws. Yeah, now the degree to which the change in reactant will affect the rate is known as the order. That order can be 0 order, 1st order, or 2nd order. So just keep that in mind. Yeah, so the order is represented by like X and Y here. That's these powers here. So again, it could be 0, 1, or 2, basically. You could have, of course, if it's A to the 0, then that's not going to affect the rate at all because the concentration is raised to the 0 power. That just gives you a 1, so the rate is unaffected. On the other hand, you could have 1st order, where as the concentration increases, the rate increases the same order. So like you double the concentration of A, then that doubles the rate. On the other hand, you could have like a 2nd order reaction. So for example, here, I think this is a little bit confusing here, this slide. Let me go ahead and just walk you through this here. This reaction is 2nd order in A. Now, if we double the concentration of A, what that's going to do is all of a sudden that's going to give us a 4x multiplier on the rate. So if we double the concentration of A and the rate quadruples, that tells us the reaction is 2nd order in A. Again, this is all stuff that we have to determine experimentally, but in the future, we'll kind of be able to predict based on what our rate limiting step is, what the rate law of a reaction should be. So just keep in mind, this is how it's dependent on concentration. The next thing that affects the rate constant is going to be activation energy. And this is basically the energy barrier that we read off of the energy diagram as we go from reactants to products. And that's basically the difference in potential energy between the reactants and this transition state. which is kind of the peak of the hill here of the energy diagram. How much energy does it take to get from the valley of the reactants here up the hill to the transition state? That difference is called activation energy, or E subscript A. And basically, like you imagine, if you increase the activation energy, that's going to decrease the number of molecules that have enough kinetic energy to actually get over the hump and form the products. And so you could imagine, you move the activation energy up, you increase the activation energy up, now all of a sudden you have almost 0 molecules that can actually make it over that hump. That reaction is going to go very slowly. Whereas if you decrease the activation energy, in other words, the molecules, the reactant molecules don't need that much kinetic energy to go, all of a sudden now all of them are just going to slide right over into the products as you decrease that activation energy. So this is how it goes. The lower the activation energy is, the faster the rate will be. And so the way that we look at that on energy diagrams is just look at the difference between the reactants and this transition state. Here, our activation energy is moderate, whereas here, now we've doubled the activation energy. It takes twice as much kinetic energy for these reactant molecules to get over this hump to form the products. So this reaction is going to go very slowly. Okay, next up, I think this is 3, temperature. Now, the other way that you can get over the activation energy is by increasing the temperature of your sample. If you increase the temperature of the sample, what that's going to do is it's going to give you a different distribution of molecules with kinetic energy. So what you do is basically at a lower temperature, this is what we were looking at before, this blue curve here. We had just a small fraction of molecules that were able to cross over the activation energy, or they had sufficient kinetic energy to cross over the activation energy. If you increase the temperature, that changes the distribution. Now we've increased the kinetic energy, so we have more molecules that have a higher kinetic energy, and a greater proportion of those molecules then have sufficient kinetic energy to break the activation energy, to go over the activation energy. So that's a way of, like, if you increase the temperature, you're going to increase the rate of the reaction, which is something that you can see easily in lab all the time. Another thing, and we've used this word before, I think this is number 4 thing that we have to consider here, which is what we call sterics, or geometrical concerns, basically. Because in order for a reaction to occur, the molecules have to collide, not just hit each other like ping pong balls or billiard balls. They actually need to be in the right orientation for a reaction to occur. So like if an electron is transferring, or let's say a proton is transferring from an acid to a base, well, the base's lone pair needs to be oriented in such a way that it can overlap with the proton of the acid so that that proton can then be transferred. Otherwise, the reaction won't occur. So if you have a big bulky base, well, that big bulky base can't really get necessarily close to the proton as easily. So that's going to slow down the reaction. It just can't fit there most of the time. So yeah, so this is the idea, this reactive conformation. If you have a big bulky, like a tert-butyl, so tert-butyl is like a big giant substituent. So like tert-butoxide, for example, is the T-butyl alcohol that has like you've removed the proton from. It's got a lone pair on it. It would make for a really good base, but it's actually like very difficult for tert-butoxide to get into different protons. So it's because this reactive conformation is very high in energy, runs into a lot of stuff. Okay, and then finally, we also have catalysts to consider. Now, catalysts we've talked about before, but it's actually going to come up a lot in organic chemistry. Because sometimes, like, there's organic reactions that could occur, sure, they'd be fine, but in order for them to occur, they have to get over a huge activation energy. In other words, the reactions have to be in just the right position to hit each other and actually produce a reaction. And if you're an organic chemist, one of our goals is like doing a reaction and making sure that we get the product that we want with as little waste as possible. And if you just leave it up to chance, like random collisions, these molecules collide with each other, they're going to form a lot of side products, you're going to end up wasting a lot of your reactants. On the other hand, you can use a catalyst, and what that catalyst does is the catalyst will bring the reactants in, it'll orient them in the proper ways or provide an alternate pathway such that those reactants can combine and form the products that you want. And so the way it does it basically is, rather than having to go straight over this hump, instead it says, hey, instead of going through this traffic jam, why don't you take the side streets over here? We've got a different route and we'll get you there to where you need to go anyways. And so yeah, this uncatalyzed reaction is the traffic, the traffic jam, and then with the catalyst, you can just go easily kind of around the side streets, a few different steps, but it's much easier, much less activation energy, and you get to where the products are. So one thing we want to keep in mind is that we don't want to mix kinetics and thermodynamics here because they are different concepts. The kinetics just tells us the rate of the reaction, and it's path dependent, basically. Like it's going to depend on this particular energy diagram, whereas the thermodynamics of the reaction doesn't change going from the catalyzed to the uncatalyzed because the thermodynamics of the products and the reactants don't change. So that's kind of how we want to compare. So like an example of like a type of comparison you may need to do is, let's say that we have A and B as reactants, and we have two separate pathways. A and B can react together to produce E and F, or they can react together to produce C and D. So there's two different considerations that we need to make. There's the thermodynamic consideration, which is the stability of the products versus the stability of the reactants, and the kinetic argument that we can make, which is like, how fast is either reaction going to go? So let's go ahead, let's look at these energy diagrams and try to parse out which one's going to be kinetically favored, in other words, which reaction is going to occur faster, and which is going to be thermodynamically favored, in other words, which produces more stable products. Well, when we put them side by side like this, it's pretty easy to see that because C and D are lower in potential energy than E and F, not only is this reaction going to be exergonic because C and D are lower in energy, but C and D are going to be the favored products thermodynamically speaking compared to E and F because they're lower in potential energy. So we're always going to favor the lower in potential energy products. So we would say that C and D are the thermodynamically favored products because they're more stable. Then looking at the kinetics, now we're looking at the activation energy. So we start from A and B here, and then for the C and D reaction, we go up to the top of this blue hill, and for the E and F reaction, we go to the top of the red hill. As we can see, the activation energy to get from A and B to E and F is much greater than it is for the activation energy from A and B to C and D. So the activation energy for the path A and B to C and D is lower. That means that the reaction is going to occur more quickly. In other words, we would say A and B going to C and D is kinetically favored as well as thermodynamically favored. What that practically means is when we react A and B together, in this situation, we expect to produce a great majority of C and D and maybe a little or maybe even none of E and F because C and D are both kinetically and thermodynamically favored. They're going to form faster and they're going to be more stable. Now, that's not very interesting, right? Because there's no conflict there. But one thing that is interesting is you can think of another example where now A and B going to C and D is still thermodynamically favored. C and D is lower in energy than E and F. So thermodynamically, you can get to C and D. You would say thermodynamically, C and D are favored. On the other hand, if we look at the activation energy here, we see now the red path from A and B to E and F is kinetically favored, whereas the activation energy going from A and B to C and D is huge. It's all the way up here now. So this is a very slow reaction compared to A and B going to E and F. So while we would say that C and D are the thermodynamically favored products, kinetically speaking, E and F is the more likely product because it's going to be the result of a faster reaction. So that's kind of how we use these words to sort of analyze this. Okay, so all right, so last thing that we want to point out here about these energy diagrams is going to be basically the difference between transition states and intermediates. These are words that we're going to use a lot during the course of the semester and into next semester. So it's important we understand that transition states, these are basically the very unfavored kind of peaks of the different hills here. These are the points where you're going from a reactant to a product, and it's like exactly halfway in between. So these are not stable, right? You can't isolate a transition state because it's not thermodynamically stable at all. It's going to either form the reactants or go to the products. Now intermediates, that's where you have this like little valley in between different transition states. So these are stable and could potentially be isolated. Maybe, not always, but frequently they can be isolated. So one thing that we want to keep in mind is we've already talked about endothermic, exothermic, and endergonic, exergonic. Another type of thing that you may be asked is like, how many steps are in this process? So in other words, how many steps to get from your reactants to your products? And one way that you can count that is just count the number of transition states. The number of transition states should describe the number of steps in the reaction that occurred. So here we have a transition state going from the reactants to intermediate 1, so that's 1. We have another transition state going from intermediate 1 to intermediate 2, so that's 2. And then a third transition state going from intermediate 2 to the products. So this is a 3-step process. And this is going to make a lot more sense because we're going to build reactions on top of one another. And when we look at mechanisms, we can describe mechanisms in terms of their energy diagram by counting the intermediates and by counting the number of reactions that we actually show. So yeah, we just want to point out here again, I mentioned this word already, but this is kind of like the last point here. The transition state is the highest energy state that a reaction is going to pass through. They are fleeting, they're momentary, instantaneous, you would say. You cannot isolate them because they are not stable. And one thing that we want to keep in mind, so these are maxima. This is the thing that we want to keep in mind. Oh, sorry, hold on. I think it's on the next slide. We'll go back to this one. 2 points that are close on an energy diagram should be similar in structure. And it also tells us basically, like, what's the relationship of the transition state to our products versus our reactants. So like here, our transition state is closer in energy to our reactants than it is to our products. So the transition state should more closely resemble our reactants than our products. In other words, the distance between carbon and bromine here as the carbon-bromine bond breaks and the carbon-chlorine bond forms should be just a little bit closer. Okay, intermediates can be observable. Just depending on the situation, you expect them to be observable, and they do exist for a period of time rather than just like being a place where it passes through. And keep in mind, these intermediates are the energy minimum. Right, okay, so, and this is what I was just talking about. If you have an exothermic reaction, the transition states are going to resemble the reactants because they're closer in energy. Whereas if you have an endothermic reaction, the transition state more closely resembles the product. All right, okay, so I hope that was helpful as a review. I think we have a few practice problems in the lecture activity. Go ahead, check that out. I'll be posting a key for that as well. And as you work through it, make sure to ask questions as you get there. And all right, I think that does it for review, I believe, for this chapter. So now we're going to move into the actual organic chemistry of this chapter, which is pretty exciting. All right, I'll see you soon.